Hello everyone, I am Harn Clark D. Salsos. So today I will discussing to you all about the recirculating aquaculture system or the RAS. So we know that the ocean of the world were long considered to be unlimited sources of the fishery product. Yet due to the rapid increase of commercial scale aquaculture, the production and per capita consumption of the fisheries product has been continuously increasing. The Chilean salmon and the tilapia are the two examples of extremely successful aquaculture products that employ intensive recirculating system at the some stage of their grow out. The Chilean salmon industry has grown from 159 million US dollar in 1991 to exporting over 2.3 billion US dollar in 2007 with 498,000 tons, while the production of the tilapia has been exponential in the last several years to the point that the US market demand for tilapia has gone from essentially nothing to importing the equivalent whole fish of 554,000 tons in 2007. Aquaculture is the most probable and feasible solution to providing the aquatic products for an ever-increasing market demand. And also, it provides a consistent and reliable source of high quality, fresh seafood that is nutritious, safe to eat, and also reasonably priced. The recirculating aquaculture system or the RAS are the key technology that will allow the world aquaculture community to supply the world per capita needs for aquatic species over the coming decades and will do so in an environmental friendly manner. So in this video, we will review the basic unit operations that make up a RAS like the oxygen supply, the carbon dioxide removal, and the nitrogenous waste management, including the biological filters for ammonia removal and the solid waste removal. The main advantage of the RAS is that the water quality can be managed to create the desired target environment for the fish being cultured instead of the environmental defining what fish can grow. There are numerous ways to design a RAS, and most people who design such a system think that their design is the best, and it should have a much better idea of how to go about designing such a system. And there is no single system that will address all needs. Design are often defined by economic constraint and availability of resources to farm owners. So the positive attributes, as the comparison, conventional aquaculture methods such as outdoor pond system and net pen system are not likely to be suitable in the long term due to the significant environmental issues and their inability to guarantee the safety of their products to the consumers. Conversely, the indoor fish production employing the RAS is sustainable, infinitely expandable, environmentally compatible, and has the ability to guarantee both and safety and the quality of the fish produced throughout the year. The indoor RAS offer the advantage of raising fish in a controlled environment, permitting controlled product growth rates and their predictable harvesting schedule. RAS converts heat and water through the water reuse after reconditioning by biological filtration using the biofilters. And it allows effective economies of scale, which result in the highest production per unit area and per unit worker of any aquaculture system. RAS are environmentally sustainable. They use of 90 to 99% less water than conventional aquaculture system or less than 1% of the land area, and they provide for an environmentally safe waste management treatment. And it allows year-round production of consistent volumes of product, and complete climate control of the rearing environment, because RAS can be set up to produce the same volume of fish every week and week out. They have competitive advantage over outdoor tanks, pond system, or wild catch, which are seasonal and sporadic in harvest. However, wrasse are almost universally employed to produce salmon smolts, and designs continue to improve that are more cost competitive with conventional aquaculture system. Recent economic studies on land-based salmon system show that salmon can actually be produced more cheaply in RAS, but the capital costs are still too high to justify the major changes in the way salmon are currently grown in the net pen system. The indoor aquaculture is probably the only potential method that could be have to ensure a 100% safe source of seafood, free from all chemicals and heavy metals. With increasing the consumer, the concern is about the food safety. The aquaculture producers using the RAS have an unprecedented opportunity to meet the demands for the safe seafood. The attributes of fresher, safer, and locally raised products are clear advantages for the RAS produced seafood. So next is the system engineering. Aquaculture engineering has come of age, and the system have been engineered specifically for aquaculture and the unique needs of an aquatic or the biological system. In addition, numerous commercial sources of equipment and supplies are now available and are specifically designed and marketed for aquaculture. Species successfully being cultivated and intensive recirculating system include the tilapia, striped bass, cobia, the pompano, and the barramundi, and the marine shrimp. So the overview of the engineering aspects in intensive recirculating system and the system component as they have emerged over the past 3 decades. First, the concept of a unit process is introduced, where a specific treatment process is used to treat the water as it is recirculated through the system. Like example, the solid removes the ammonia converted into nitrate, oxygen added, carbon dioxide removed, and in some cases, if necessary, disinfected. Then, the example of treatment technologies currently used are described in linked together within a complete recirculating system design. And finally, a design example uses the engineering concept of mass balance to show how the estimate water flow requirements for oxygen, the ammonia removal, the solid waste removal, and carbon dioxide removal. So this is called the unit processes, which correspond to a specific treatment process. As you can see the figure, it shows how a recirculation system can be subdivided into several individual units or processes that may correspond to separate the system or to be linked together in a process stream. So the process flow diagram in the figure, the water moves from the central fish culture tank and flows through the system that remove the suitable and suspended waste solids. Remove the fine and dissolved solids, convert the ammonia to nitrate, then remove the carbon dioxide and add oxygen, and finally, when required, disinfect the water before returning it to the culture tank. The monitoring and control system oversees all of these processes and control the set points of the water quality and sound an alarm if they move outside of acceptable ranges. A biosecurity program and process must be absolutely superimposed on the whole process and farm to prevent losses due to the disease introduction from the outside. In a real-world system, the individual unit processes are usually linked together as the water flows through each process or the recirculation. Usually, 10 to 20% of the discharge flow from a culture tank is removed from the center drain to take the advantage of the teacup effect, which concentrate the solid to central drain flow. There are some form of suitable solids removal device like swirl separator, the radial flow clarifier, settling basins pretreats this flow stream, which which is then combined with the remaining 80 to 90% of the discharge from the side outlet. This combination of center drain and sidewall drain is usually referred to as a Cornell dual drain system. The remaining suspended solids are then removed usually by either a rotating microscreen filter or floating bead filter. Next is the culture tanks. People have used a wide variety of material to construct tanks, including just about anything that holds water. Simple molded polyethylene tanks are often used due to their low cost, smooth surface that makes for easy cleaning, and their low weight, which allow for quick setup and relocation. They work well for the most part, but because they are very soft and malleable, and they need to be well supported on the bottom. The fiberglass is the most popular choice for tanks because it is flexibility in both size and shapes. Fiberglass is the popular choice for tanks because of its flexibility in both size and shapes. The fiberglass tank panels are easy to cut, drill, and modify, and repairs are relatively easy. Large fiberglass tanks come in easily transported components that are field assembled and almost any diameter. The bottoms are usually poured concrete where the drains and heating coils are embedded, along with the tank sidewall. Tank can be partially buried to conserve heat and make fish observation easier. The concrete is always an option in making the tanks. It is extremely strong but very permanent. Mixed cell raceway design are another option for tank design, combining the advantages of a raceway for grading and sorting and round tank for solid removal. To promote mixing and solids removal, it is important that a tank has good hydraulic characteristics. One of the most important rules for RAS is that solids need to be removed from the tank as quickly and efficiently as possible to reduce the solids' impact on the water quality. Tanks can be characterized by diameter, the capital D to depth, then the small d ratio, which is depth per ratio. This ratio should be maintained greater than 3 and less than 10 and preferable less than 5 as in the deeper tank given the same diameter. Using this range of depth per ratio will minimize the problems of solid settling. Before reaching a center drain, indicating that a tank is too shallow, that is an excessive depth per ratio, or not settling fast enough to reach the drain by being continually resuspended, indicating a silo type tank that is too deep and that is too small for a depth per ratio. Next is the waste solids removal. Waste solids are produced in an aquaculture system as eaten feed, feed fines, fish fecal matter, algae, and slough biofilm cell mass from biological filters. The waste solids influence the efficiency of all other unit processes in the recirculating system, and they are a major source of carbonaceous oxygen demand and nutrient input into the water, and can directly affect fish health within the recirculating system. Therefore, solids removal is considered one of the most critical processes in aquaculture system. Optimally, solids need to be removed from the fish culture tank as soon as possible, with the minimum turbulence of mechanical shearing. Solids are generally classified into three categories: the settlable, suspended, and fine or dissolved solids. In recirculation system, the two are the primary concern. The waste solids can be removed either settling with the culture unit or through the use of the solids removal unit. Following following rearing tank, the several unit process options are currently being used in aquaculture. Settling basins and the radial flow clarifiers, the mechanical filters, the granular media filters, and the flotation or foam fractionation. Next is the Cornell dual drain system. The Cornell dual drain system uses the culture tank itself as a swirl separator, the teacup effect, and remove most of the settlable solids from the small percentage of the discharge from the center drain. The design system is applicable to the round tanks, and it is very effective in removing the majority of large, quickly settleable solids such as uneaten feed and the fecal matter, using only the small portion of the total water flow, with the 10 to 25%. This waste stream can then be further concentrated using either the settling basins or additional swirl separators. Remember, the objective is to create a small, concentrated flow that is easily treated, rather than a large with the diluted flow of waste. Solids that concentrated at a bottom center can be removed in a small flow stream by using the bottom drawing center drain, while the majority of the flow is withdrawn at an elevated drain. The dual drain system uses a center drain that removes from 10 to 25% of the flow and a higher sidewall drain for the majority of the flow. So as you can see, a design criteria for the percentage of flow that should be minimally be removed by the center drain are 6 lpm over the meter squared, or with the 0.15 GPM per feet squared of the tank floor area. The hydraulic retention time, or the RHT center drain, is less than 200 minutes and 15 to 25% of the total tank flow rate. After calculating these three values, the largest of the three values should be used. A final criterion that should be applied to the drain design outlet is that the tank outlet should be approximately 10% of the tank diameter. This is because of the DD ratio. Recommendation is the followed. Then solid should be settled on the floor within 5% of the tank diameter of the tank center drain and be removed. For example, if a tank were in 10 meter in diameter, the center drain should have an effective diameter of 1 meter by using a flat plate slightly elevated above the tank floor, and the solids will be settled within 0.5 meter of the center point of the floor of the tank floor. Thus, this solid would be drawn into the center drain by high velocity created by the flow out of the center drain. By concentrating the majority of the solid waste in only 10 to 25% of the flow leaving a tank via the center low flow drain treatment, costs are proportionately reduced as well. Next is the settling basins and tanks. A settling basin is simply a tank that provides a quiet, non-turbulent area where the flow rate is low and the solids are allowed to settle out the suspension by gravity. The advantage of settling basins are simplicity of operation, the low energy requirements, and their low construction costs. The disadvantages include the large size of settling basins, their low removal efficiency of small or low density particles, and leaching of nutrients from the settled solids back into the system while the solids are stored in the settling basin. Another method to increase the sedimentation rate is through the use of swirl separators, or the hydrocyclones, and these have most often been used in aquaculture circulating system to concentrate the solids from the dual drain culture tank system. Next is the mechanical filters. There are two types of mechanical filters are commonly used in aquaculture to remove the suspended solids: the screen filters and the expandable granular media filters. The suspended solids from an aquaculture viewpoint are within the fraction of total solids that will not settle out of the water column in a reasonable amount of time within the 30 to 60 minutes. This fraction of solid waste needs to be removed from the culture tank water because of its potentially high oxygen demand and the mineralization, with the increased rate of ammonia nitrogen being added to the water column as the protein and the urea in the feces is broken down by the bacteria into ammonia. Microscreen are used to remove suspended solids, both research and commercial recirculating system, and it acts as a form of sieve that retains suspended particles larger than the fine mesh filter screen openings. The rotating microscreen filters, in a variety of size and flow rate capacities, they have numerous advantages. The number one is the primary one, being that they are easy to install and operate. Almost all microscreen filters work on the principle of the physical interceptions of particles on screen and their removal by means of a water spray. The microscreen are especially attractive when used to remove solids from large flow streams, and they are compact in size and cost in minimal head loss. The disadvantage of these systems are high maintenance requirements and the relative high capital and operating costs. The performance of the microscreen filter is largely dependent on the size of the filter screen openings, influencing the filter's hydraulic capacity, the fraction of particles removed, and also the sludge water production rate and the concentration, and also the filter backwash frequency that is generally discharged from the system, with the water loss that must be replaced. Next is the granular media filters. The granular media filters operate by passing the water laden with the suspended solids through a bed of granular material, which traps the solids through the sedimentations, straining, and interception. The bead filters are the most popular form due to their low head loss and low water requirements for backflushing. The bead filters have replaced to use the sand filters for all practical purposes. While the sand filters can do a super job at removing the solids, where typically a sand bed is flooded from the top of the water is allowed to percolate through the sand. Sand filters, such as those used in swimming pools, to operate under the same principle but use the water pressure to force the solids laden the water through the sand. So the bead filters employ small 3 to 5 millimeters low density. So this type of plastic media is commonly used as feedstock for plastic injection molding process. So these filters have been successfully used for both solids capture and biofiltration. Traditionally, the disadvantage of this type of filter has been a large of volume of water required for backflushing, with although much is less required than the sand filter design. Although the polyjacer class of bead filters have successfully addressed this problem. So the suspended solids and the dissolved organic compounds is that build up of over the time in intensive recirculating system that are removed by the mechanical filtration and the granular media filters. These solids can be removed by the using a process usually referred to as a foam fractionation, air stripping, or the protein skimming. In this process, The air bubbles rising through a close contact column physically adsorb the fine suspended solids and the dissolved organic compounds onto the surfaces of the air bubbles. So the bubbles create foam at the top of the liquid column, and the organic wastes can be disposed of along with the foam produced. So next is the disposal of the solids. In general, aquaculture solids waste are treated as an agriculture waste and considered a non-toxic nutrient source. The land application of the waste solids on the on-site, the agricultural fields, is usually the cheapest methods of the solids disposal. The land application is governed by the regulation that limit the amount of pathogens, heavy metals, and other contaminants such as nutrient content, soil type, and plant nutrient uptake. The characteristic is to prevent the runoff or the groundwater contamination. So one of the newest techniques for containing sludge is to use the geotextile bags. So these are porous textile bags that are receive the waste stream and the capture solids while allowing the water to drain off for recapture. In many cases, a polymer or the flocculation agent is added to the influent to improve the solids per liquid separation. Alum or the ferric chloride can also be added as a coagulation aid, which also help to sequester the dissolved phosphorus. Composting of waste solids using the thermophilic bacteria creates a valuable soil amendment and also can be used to dispose of fish mortalities in a safe manner. The anaerobic and the aerobic waste will require carefully engineering design to be properly sized and managed. So next is the biofiltration. The nitrogen is an essential nutrient for all living organisms and it is found in proteins, nucleic acids, adenosines, phosphates, the pyridine, nucleotides, and also the pigments. So there are four primary sources of the nitrogenous waste. The number one is the urea, uric acid, and the amino acids, which excreted by the fish. And the second is the organic debris from the dead and the dying organisms. The third is the uneaten feed and feces. And last is the nitrogen gas from the atmosphere. So there are various nitrogenous waste products are expelled by the fish through the gill diffusion and the gill cation exchange with the urine and the feces. The decomposition of these nitrogenous compounds is particularly important in intensive recirculating aquaculture system because of the toxicity of the ammonia, the nitrite, and to some limited extent with the nitrate. So the reverse process is called the denitrification and is an anaerobic process where the nitrate is converted into nitrogen gas. The denitrification process is becoming increasingly important, especially in marine systems, as stocking densities increase and the water exchange rates are reduced, the resulting in excessive levels of the nitrate in the culture system. The ammonia, nitrate, and nitrite are all highly soluble in water. Ammonia exists in two forms, the unionized and the ionized, with the relative concentration primarily a function of pH and the temperature. The nitrification is a two-step process where the ammonia is first oxidized to nitrite and then the nitrite is oxidized to nitrate. So the two steps in the reaction are normally carried out sequentially. Since the first step has a higher kinetic reaction than the second step, the overall kinetics are usually controlled by the ammonia oxidation. and as a result, there is usually no appreciable amount of the nitrite accumulation. So as you can see in the equation 1, 2, and 3 show the basic chemical conversions occurring during the oxidation by the nitrosomonas and the nitrobacter and overall oxidation reaction. The alkalinity is measured or defined in terms of the calcium carbonate is generally added by the using sodium bicarbonate or the baking soda or the calcium carbonate and the slake lime or the hydrated lime. Sodium carbonate has the advantage of being rapidly dissolved and being very safe to handle, and you can eat it if your stomach is upset. So the ammonia removal capacity of the biological filter is largely dependent upon the total surface area available for being biological growth and the nitrifying bacteria. The media used in the biofilters must be inert, non-compressible, and not biologically degradable. The typical media used in aquaculture biofilters are the sand or some form of plastic or the ceramic material shaped as small beads or large spheres, the rings or the saddles. Biofilters must be carefully designed to avoid the oxygen limitation or the excessive loading of solids, the biochemical oxygen demand, or the ammonia. There are several types of biofilters commonly used in the commercial intensive recirculating aquaculture system are the trickling biofilters, the floating beads filters, the fluidized bed biofilters, the downflow microbed filters, and the moving bed bioreactors or the MBBR. Next is the fluidized sunbeds, usually used in the large-scale cool or cold water application. The fluidized sunbeds provide a large surface area for bacteria in small footprint. This filter get their name because as the water flow up through the sunbed, the sand becomes suspended in the flow or fluidized. So, the fluidized sunbeds can be relatively more expensive to operate than the other filters due to high pump rates and the pressure required for the fluidize the sunbed. And the trickling towers are the classical biofilter, combining both biofiltration, the aeration, and the degassing into one unit process, and they can be constructed to any diameter required. So the media both horizontally and vertically is a continual challenge. The downflow microbreed filters have been used for several years due to their simplicity and the low cost for media. The filter uses a small plastic beads into 1 to 3 millimeters that float in the biofilters as the water flow down through them. The styrofoam microbeads are also a fraction of the cost of the other bead media. Floating bead filters use beads that are slightly buoyant. The beads provide surface area for the bacteria and also trap solids. The backwashing of the filter is accomplished either mechanically with a motor or the propeller or with air bubbles. A desired backwash or mixing cycle, after mixing and breaking up the starting floating bed, the bed is allowed to settle for a minute, and then settled sludge is discharged by opening a valve at the bottom of the filter, and will be imposed to clean the beds and remove the resulting sludge. Newer design for bead filters have a capacity to minimize the water loss during the cleaning cycle. The advantages of in marine system where the loss of salt water is minimized and thus operating costs are decreased. The moving bed bioreactors or the MBBR have been introduced over the last several years and appear to be one of the most competitive of all biofilter types. The media remain in suspension as the water flows through the biofilters, which are actively aerated. The high turbulence and aeration provide a good mixing and contrast with the media. The choice of biofilter. Each biofilter described has advantages and disadvantages. One of the chief advantage of both the trickling biofilter and the MBBR is that they both add oxygen to the water flow during the normal operation, and they can provide some carbon dioxide stripping. In contrast, the submerged biofilters, the floating bed filters, microbed filters, and the fluidized bed biofilters are all net oxygen consumers and must rely solely on the oxygen in the influent flow to maintain the aerobic condition for the biofilm. So the application of low-specific surface area media is the distinct advantage for both the trickling biofilters and the MBBR. Since the capital cost is proportional to the total surface area of the filters, the result is physically large and requires more costly filters. In contrast, floating bed filters, and especially the fluidized bed filters and the downflow micro bed filters, use the media with high specific surface area, resulting reduce the cost and space requirements for the equivalent surface area. The aeration and oxygenation. The dissolved oxygen is the first limiting factor in intensive aquaculture system. The minimum dissolved oxygen are required for optimal growth and survival of the most aquaculture species. Aeration with atmospheric oxygen is the adequate to maintain the level and is commonly referred to as aeration. At higher stocking densities, pure oxygen is required and usually referred to as oxygenation. In the oxygenation process, pure oxygen is used to increase the transfer rate in the yield supersaturated oxygen concentration, theoretically 5 times that of the aeration with the atmospheric oxygen. And oxygen can be produced on site using the pressure swing adsorption or the PSA. The equipment or the purchase in bulk liquid or gas form from the commercial sources. Numerous types of oxygen transfer equipment are now available from the commercial sources, including U-tubes and multi-stage low-head oxygenation units, the pack columns, pressurized columns, the oxygenation cons, and the oxygen aspirators, the bubble diffuser, and enclosed mechanical surface mixers. The two most often used in large-scale commercial systems are the downflow bubble contractor, so which is the space cons as you can see in the figure, or the multi-stage low head oxygenation or the LHO unit. The downflow bubble contractor or space cone consists of a cone-shaped column with the water and oxygen injected at the top and removed at the bottom. A multi-stage low-head oxygenation unit or the LHO increases oxygen transfer efficiency by reusing the oxygen feed gas through the series of a contact chamber. The water flow is distributed equally through a series of chambers via a perforated plate. Flow flows through the chamber and into a pool of water, which seals the lower outlets. The LHO provide moderate oxygen transfer efficiency and operate at very low pressure heads. Gas to liquids ratio should be maintained less than 1.5% to obtain the reasonable transfer efficiency with a 70%.